Welcome to this video lecture on property plots and tables. So in prior videos we've been talking about the first law, work, heat transfer, and in that first law expression, if you recall, there's a total energy term that involves internal energy, kinetic energy, and potential energy. So one question we might have is, how do you find that internal energy term? Well, we're going to talk a little bit about that today, as well as how to find some other properties that we'll cover in more detail in future videos. So let's go ahead and get started. Take a look at your screen. So on the screen here you see a picture of an iceberg. And the reason I show this is because in the image you see ice in two forms. I'm sorry, water in two forms. You see water as a solid, namely ice, as well as liquid, which is the water part. And actually, in the atmosphere, there's also water vapor, so there's actually three different forms for the water. Now, you're probably familiar with these three different phases of matter, so solid, liquid, and vapor. And in this course, we'll focus primarily on the liquid and vapor phases. We'll talk about solids here and there, but it's mostly the liquid and vapor phases that we'll focus on. So I thought this was a nice representative picture to motivate the work. So let's get started. Now, the first thing we're going to take a look at is phase plot of a typical substance. So you can see two images here. They're basically the same kind of plots. The one on the left is for a substance that contracts upon freezing, and the one on the right is one that expands upon freezing. So the one on the right would be something like water. Water is kind of special because it expands when it turns into ice. Most substances behave this way, where when they become solid, they contract. And these are called phase plots, or PVT surfaces, so pressure, volume, and temperature surfaces. And what they do is they show the different phases of a material depending on those three properties. We're going to be focusing in this course on pure substances, which means that there are no chemical reactions occurring in the substances. We'll also focus on simple compressible systems, which means that any two independent properties can uniquely identify the state. So you could use, for example, pressure and temperature to identify the state of the system, or temperature and specific volume. Any two independent properties can specify the state in general. So simple compressible systems, the ones that we'll be focusing on will be pure water, as well as mixtures of gases that don't react. Okay, and far from the mixture of gases will be far from the point at which they condense into liquids. So we don't have to worry about some components condensing while other components don't. They just remain as gases. Okay, so in these plots, I want to identify just a few regions of interest. So here you see pressure, specific volume, and temperature on the three axes. You'll see regions that consist of single phases. So we have solid region here, liquid region here, gas region here. And then we also see regions where you have mixtures. So here's a solid and vapor region, solid liquid region, liquid and vapor region. And there's another point here called the critical state. Above this point, the liquid and vapor phases become difficult to distinguish. In fact, you just have what appears to be essentially like a very viscous gas. So that's above the critical state. We'll come back to that in just a little bit. In addition, on this plot, you'll see some lines here. So here's a constant pressure line, this sort of green dashed line. That's called an isobar, just means a constant pressure. And then you have a constant temperature line here. That's called an isotherm, so just constant temperature. One thing that you'll notice in on those lines is that they remain constant in this region here, this liquid vapor region. We're going to focus on that one in particular in our future studies. And that's what we call the vapor dome. It's a vapor dome because it looks like a dome shape. And in that vapor dome, you'll see that the pressure and temperature are connected to one another. So we'll talk about that a little bit later. There's also another line in here called the triple state line. And on that line, you actually have all three phases of matter. So liquid, solid, and vapor all existing in equilibrium with one another on that triple state. You see the same kind of behavior on this plot to the right, all the same features and such. The only thing that's different is the slope of this solid liquid kind of line here. You see it's kind of going into the picture here. Here it's coming out of the picture. So that's the difference between a substance that contracts upon freezing versus one that expands upon freezing. Now, looking at these kinds of plots, it's difficult to really analyze them in a lot of depth because of the three-dimensional nature of it. So it's a little easier to look at them from a 2D perspective. So that's what we're seeing here in this image. This is a phase diagram for water where we're looking at the pressure temperature axes. So it would look like looking from this point of view here, where we're just looking in from the side. So we have temperature, pressure, specific volume would be into the page. And so this is one specifically for water, a substance that expands upon freezing. And so you can see here's the solid region, the vapor region, and the liquid region. When you cross from a solid to a vapor, so going this direction, that's called sublimation. So you're going directly from a solid phase to a vapor phase. When you go the other direction, from a vapor to a solid, it's called desublimation. Not a very imaginative name, but it's descriptive nonetheless. When you go from a solid to a liquid, that's called melting. You're familiar with that. And then when you go from a liquid to a solid, that's called freezing. You're familiar with that as well. And then when you go from a liquid to a vapor, that's vaporization. And then from a vapor to a liquid, that's condensation. The triple line, so if you go back up to this picture, you'll see that you have this triple state that goes straight along the specific volume axis here. And so when you're looking at the temperature, pressure axes, it becomes a triple point. Again, that's the point where you have all three phases is existing in equilibrium. And it's just at a very specific pressure and temperature. Okay? And then you can also see the critical point here. That's also at a very specific temperature and pressure. And again, above that critical point up in here, the liquid and vapor regions become indistinguishable, and you deal with essentially a vapor with a very high viscosity. Okay, now in our analysis, we won't really use this kind of point of view very often, the pressure temperature axes. Instead, we'll use pressure specific volume and temperature specific volume axes. So those are given down here. So here is, let me just kind of focus on this picture here. This is again for water. This is a pressure axis. This is given in bars. This is an absolute pressure here. In a lot of these tables and plots that I'll be showing, it doesn't distinguish whether it's a gauge pressure or an absolute pressure, but they're all absolute pressures. So just keep that in mind, that that's an absolute pressure. And then on this axis, we have specific volume in cubic meters per kilogram. One thing to notice is that this is a log axis, and that's a log axis. Okay? And then on this plot, we're only focused on the liquid vapor regions. We're not going to worry about solids mostly in this course. It'll just mostly be liquid and vapor. And the reason for that is because of a lot of the power generation cycles, refrigeration cycles, and heat pump cycles that we deal with just involve liquid and vapor. They don't really involve solids at all. So our emphasis will be on the liquid vapor and liquid vapor mixture regions. So again, if you go back up to this picture, you'll see we have this vapor dome with liquid and vapor, with liquid to one side and vapor to the other side. So what we're going to do now is, since we're looking at the pressure specific volume axes, we're going to be looking in from this side. So if we do that, that's what this picture looks like. So pressure, specific volume. The vapor dome is this line that I'm kind of sketching out here, skewed to one side. So inside here, this is a saturated liquid vapor mixture region. So this is saturated liquid vapor mixture. Over here is vapor, and over here in this kind of smashed in region is the liquid. Okay? The critical point is right there, so that's the critical point. I'll just abbreviate it as CP. And there are certain features on here I'm going to identify. this line that goes from the critical point down and separating the liquid vapor mixture region. So in this region here, we call this the vapor dome. In that vapor dome, liquid and vapor exist in equilibrium. So you can have a mixture of liquid and vapor totally fine. So that's inside. It's kind of like when you're boiling water, right? When you're boiling water, you have vapor water as well as liquid water simultaneously. So that would be in the saturated liquid vapor mixture region. Okay, so that's this region here inside the vapor dome. And then this line that goes from the critical point all the way down that separates the saturated liquid vapor region from the liquid region, that is called the saturated liquid line. So that's this kind of blue line here. Okay, so that's this point, that's that line right there. And then the line that's separating the saturated liquid vapor mixture region from the vapor region is this red line that goes down this way. So that's this line right here. So those lines represent when you have, on the blue line, it's right at the boundary between liquid and a liquid vapor mixture region, but it's still 100% liquid. Okay, so it's just saturated liquid. It's almost liquid and vapor, but it's just right at the boundary, but it's still 100% liquid. And then the red line is the boundary when you're almost at the liquid vapor mixture and vapor, but it's 100% vapor. Okay, it's still, and by vapor I mean it's well, it's like steam, right? For water it would be steam. That's water vapor. So it's right at the boundary between being a mixture of liquid and vapor, but it's 100% vapor, so we call it saturated vapor. Now the lines that you see in this plot are isotherms, and so that you see the various temperatures here. So an isotherm, let me just kind of highlight one of those. You'd come down here, this is the shape of an isotherm in this plot. Okay, so you can see this is a constant temperature line that's highlighted by the green there. Okay, and what you'll see here is that as you follow that constant temperature line, or that isotherm, in the vapor dome, the isotherm remains horizontal. It stays constant. So it stays at a constant pressure when you're inside the vapor dome. Okay, so as you're changing the specific volume and you have the liquid vapor mixture, the temperature remains constant and at the same, and the pressure remains constant inside there. Okay, that's something we'll come back to in a moment. So that's what a real PV plot looks like, so PV diagram for water. It's a little awkward to try to sketch that out, to scale in reality. So a lot of times we'll just do a really rough sketch, which is what I'm showing in the picture above. This is still a pressure specific volume plot. I'm just drawing all the same features here. We have our vapor dome, right? Of course, I've just kind of sketched it roughly. It's not exactly, the real shape here. But this is the form this is the kind of sketch I'll do frequently, and you can do it this way as well. But you just have this vapor dome. Here's the saturated liquid line. Over here we have liquid. By the way, another name that we give the liquid region is we call it a compressed liquid. Okay, so that's just a terminology. Compressed liquid just means liquid. Okay, so that's the compressed liquid or liquid region. Over on the other side, let me change the color just to be consistent here. So we'll call this compressed liquid. Then over here we have vapor. So that's that region, or superheated vapor is another name for it. So let me do that way. Superheated vapor. So you can see that's this one. Compressed liquid is that one. So superheated vapor just means vapor. It's again just a terminology term. Just a terminology thing. You'll hear superheated vapor and compressed liquid. It just means vapor and liquid. Inside the vapor dome, we have the saturated liquid vapor region. Let me put that in a different color. Saturated liquid vapor mixture. So that's where you have liquid and vapor existing simultaneously in equilibrium. And then let me go ahead and sketch in an isotherm in green. Let's do it this way. So an isotherm here would look like this. So that's the isotherm, where the temperature remains constant. It looks like that. And let me just draw in a couple of them. Again, these are not to scale. And then let me draw one up here. These are not to scale. To scale, it's down here. This is what it really looks like to scale down here, but this is just a sketch. So these are isotherms, just different temperatures. And going this direction is temperatures increasing. Okay? This point right at the very top is the critical point, CP. So that's this one right there. So that's what the pressure specific volume plot looks like for a substance like water, for example. So that's just kind of a rough sketch, and this is the kind of sketch we'll use all the time. Again, the blue line here, just as a reminder, is 100% liquid. This one is 100% vapor, and they're called saturated liquid and saturated vapor. All right, let's see if there's anything else I want to mention on this one. Let me take a look at my notes. Actually, let me just talk a little bit about, well, I'll do it on the next plot. I'm going to talk a little bit about boiling of water, but I'll do that on the next one. It's a little more clear. So I've shown this here for pressure specific volume axes, but we can do the same kind of idea. Instead of pressure specific volume, we can do temperature specific volume. So it would be like looking down from the top onto this plot. And you still have the appearance of the vapor dome and such. So let's go ahead and sketch that one out. So that will look much the same. Let me do the rough sketch first, and then we'll do what it really looks like. So here's temperature on this axis, specific volume on that axis. We still have the appearance of the vapor dome with the saturated liquid line, saturated vapor line. We still have a critical point. We still have the saturated liquid vapor mixture region. This is the compressed liquid. This is the, let me change the colors. So this is compressed liquid. This is the superheated vapor over there. And then I'm going to draw an isobar on this plot. So on the previous one, where it was a PV plot, I drew isotherms, lines of constant temperature. Here in the TV plot, I'm going to draw isobars, which are lines of constant pressure. So those will look like the following. So these are typical sketches of isobars, where the pressure is a constant. Okay, and as you go this direction, pressure increases. So those are isobars. Now, it's easy to get confused. You know, does an isotherm go, you know, from the upper left to the lower right, or do isobars do that? You know, it's kind of hard to remember. So I have a little kind of silly mnemonic, not really a mnemonic, but a little graphical way that I remember this. And I'm going to share it with you. It's kind of silly, but you'll remember it if I show it to you. If I write isotherm, first of all, you have to be able to spell isotherm. And then let me write isobar. If you notice on therm, on the M, it drops down, right? So and when you write out the letter M, it drops down. And when you write out isobar, when you write out the R is up, moves upward. And so when you draw an isobar, it moves, as you go from the left to the right, it goes upward. See how it's going upward here? Just like the R is going upward. Whereas for an isotherm, the M is going down there. So when I sketch an isotherm here, as you go from left to right, it goes downward, just like the M. So that's how you can remember it very easily. It's kind of silly, I know, but it works. So isotherms go from the upper left to the bottom right, just like the M does. And an isobar goes from the bottom left to the upper right, just like the R does. Okay, so that's an easy way to remember it. Now, if you want to see what the real plot looks like, on a TV plot for water. That's this picture here. Again, this is the real picture. You can see the vapor dome here. So this is the saturated liquid vapor mixture region, saturated liquid vapor mixture. You have your compressed liquid over here. You have your superheated vapor over here. Here is your critical point. And then, of course, you can see isobars sketched out here. These are all absolute pressure. So you see the isobar comes up, goes over, and then continues up over that way. So this one's to scale. Here you can see the temperature is a linear scale. Specific volume here is a logarithmic scale. Again, it's kind of difficult to sketch it perfectly, so that's why I draw these kind of rough little sketches. You'll see these all the time. Okay, now one of the things I wanted to highlight was, let's just kind of sketch out what happens when you boil water at 1 atmosphere. So we're here, standard temperature and pressure, kind of sea level, right? And so that would be pretty close to 1 bar. So let me highlight that. All right, so 1 bar goes like this. There we go. And so let's just kind of sketch out what happens when we boil water, okay? So when we boil water, we're going to start at a low temperature down here, like right about in here, so maybe 20 degrees Celsius. So we'll go along that 1 bar, maybe it's that isobar there. So we start there, and then we start adding energy into our pot of water via heat transfer. So that's going to increase the temperature of our water. So that moves up. So where the temperature is going up, we're still at 1 bar because it's still just at 1 atmosphere, right? 1 bar is pretty close to 1 atmosphere. So we're just increasing the temperature. The water actually increases its specific volume only slightly, just a very small amount. You can see as we move up that isobar, you know, we don't move too far to the right in our specific volume. We do move to the right a little bit, but not a whole lot. So the water is expanding a little bit, right, because it's taking up more volume per unit mass. And then we hit the saturated liquid line. Oops, excuse me there. So then we hit the saturated liquid line right here. Okay, so we moved up along that isobar till the temperature at 1 bar where we hit the saturated liquid line is at 100 degrees Celsius, right where we expect it to boil. Right? And so now we have a saturated liquid, and as we continue to add energy into our boiling pot of liquid, what happens is we move, as we're continuing to add energy, we continue to move this way on the specific volume axis. So now we're going this way on our plot. So we still stay at 1 bar because the atmosphere is still just 1 atmosphere, right? It's just roughly 1 bar. We're not changing altitude or anything like that. So it just stays, and our pot of water that we're boiling is uncovered, so its surface is at roughly 1 bar. But what ends up happening is the volume, specific volume, starts to increase considerably, and that's because we're now adding vapor into our mixture, right? So it starts off as almost pure liquid, and then as it starts to boil, you're getting these bubbles of vapor that are forming. So now we're starting to get a much larger specific volume. And so the specific volume is going this way. And as we move to the right, what's happening is we're getting more and more vapor. So it starts as mostly liquid, and now it's starting to become more and more vapor as we move along in the saturated liquid vapor mixture dome. And during that whole process, the temperature actually remains constant. So as you boil water, it's always at 100 degrees Celsius as it's boiling. Temperature doesn't go up. So even if you have a small, kind of gentle boil or a very vigorous boil, that water's still at 100 degrees Celsius. It stays that way. Because what's happening is as you're adding energy into the liquid phase, liquid vapor phase, that energy is not going to raise the temperature of the mixture. What it's doing is that energy is going into changing the phase of the mixture. It's going to change liquid into the vapor. And so that's why we're moving here at a constant temperature. And then eventually we'll reach a point where we hit the saturated vapor line. So now that mixture is just 100% vapor. At that point, as we continue to add in more energy, now we go into increasing the temperature of the vapor. It's all pure vapor. There's no phase change occurring any longer. It's 100% vapor. So we continue to add energy, the temperature of the vapor will start to increase. And so that's why we're moving up this way. So you can see that the temperature over here is increasing as we continue to add energy. And not only that, we're also increasing the specific volume at the same time, right? So the specific volume is going up as well. So that's the process of boiling. So you can see the thing I really wanted to highlight was this constant temperature region under the vapor dome that occurs as you're doing the change of phase. And that's a similar set of arguments can be used to describe why you have, in this PV plot, why the temperature remains constant at a particular pressure. So here, by the way, you can see at 100 degrees C, that's occurring at roughly 1 bar. Again, this would be the point at which you're boiling water at roughly 1 atmosphere. Okay. All right. So these plots are very instructive for us when we're kind of sketching out processes. So we'll use these frequently to identify where we are in terms of a state. If we're dealing with water, are we dealing with a saturated liquid vapor mixture? Are we dealing with a compressed liquid? Are we dealing with superheated vapor? We'll just put points in here roughly to kind of indicate where we are in terms of our state, and then we'll draw lines on them on these plots. So for example, if I was going to sketch out a particular process, maybe I'm starting here and going like this. Maybe I have a process that looks something like this. I'm just kind of sketching something out that's rough here. Maybe that's a particular path that I'm following for some big process or some cycle. And so we use these plots to kind of sketch that out so we can just keep track visually of what we're doing, okay, and what kind of phase the substance is in. So we'll do that a lot in the course, and you'll see examples of this. But it's very difficult to pull out exact numbers, to be quantitative from this. You could try to pull numbers out from this kind of a plot, but it's difficult to do. This is a log axis. That's a log axis here. It's going to be difficult to be precise using a plot like that. So instead of using plots to get quantitative information, we use tables of values. So all the data on this kind of a plot, as well as this kind of plot, we have that data in table form. So here is an example of this kind of table. Now, by the way, these tables were generated using property values from NIST. NIST is the National Institute of Standards and Technology, and it's the U.S. government organization that does a lot of property measurements and techniques for measuring properties. So all the data you see in the table here comes from NIST-generated data. And I give in the lecture, I think the lecture reading, at least my notes, a link to where you can find that kind of data. So this is just an Excel spreadsheet that summarized that data from NIST. And so what this table is the saturated liquid vapor mixture table, organized based on temperature. And so what I mean by that is here you have temperature going down this axis. This is the corresponding pressure. So for example, let me pick a temperature of, let's say 20 degrees Celsius. The pressure is about 0.02 bars. So let me go back up to this plot here. It's a little hard to see. Well, actually, maybe I can pick a different number. Let's see what I've got here. Well, 20 is about as good as it's going to get. So here's roughly 20 degrees Celsius. And you can see the corresponding pressure in the vapor dome where we have the saturated liquid vapor mixture. Okay? So here is the corresponding pressure at that given temperature. Okay, so that's how you read this. Here's the temperature. Here's that corresponding saturation pressure at that particular temperature. This is inside the saturated liquid vapor mixture region, or underneath the vapor dome. Now you'll see some other properties listed here. So you have properties for liquid, properties for vapor. Now what these are the properties along the saturated liquid line and the saturated vapor line. So these are, notice this is in blue and this is in red. So these correspond to the properties along this line for the liquid part, and then this one for the vapor part. or if you'd rather, this one for the liquid part, and then this line for the vapor part. So if you wanted the specific volume along that saturated liquid line at 20 degrees Celsius, that would be the specific volume. If you wanted the internal energy, now I mentioned at the beginning of this video lecture, we're now going to start telling you how to find that internal energy property. That internal energy is found from this table, namely specific internal energy. You'll notice the units are kilojoules per kilogram. And so along the saturated liquid line, the specific internal energy value is right here, 83.912. And then we have these other two properties, enthalpy. This is actually specific enthalpy and specific entropy. We're going to talk about those later, so don't worry about them right now. Similarly, we have properties for the saturated vapor, right? So that would be along this part of the vapor dome. And so if you wanted the specific volume for the saturated vapor at 20 degrees Celsius, we'd come over here and you'd see it'd be 57.757 cubic meters per kilogram. So again, that's the specific volume. These are all specific quantities: specific volume, specific internal energy, specific enthalpy, specific entropy. You'll notice the subscripts here. There's an F subscript in this one and a G for this one. That's just, again, notational. The F, you can think of it as fluid. It's not a very precise thing, but it's really the liquid. The G, you can think of it as gas. Again, it's really vapor. I'll actually often use the subscript like V sub L and V sub V for liquid and vapor. But you'll see it as F and G as well. Okay. So one question you might have is, well, this is all fine and good for finding out what the saturated liquid and saturated vapor values are, but what about in between, right? All I've done so far is talked about how to find the properties along this line and the properties along that line. But what about everything in between? That's going to be saved for the next lecture. For that, we have to use another quantity called the quality. The quality tells you what fraction of your mixture is vapor and what fraction is liquid. So, and it's just a linear combination of the properties of the two. But we'll focus on that in the next lecture. For now, all you really know how to find are the properties along that line and the properties along that line. Next lecture, we'll worry about how to find properties on the inside. So that's a saturated liquid vapor mixture table organized according to temperature. One other thing I should just identify, and by the way, the picture here, the table is just a snapshot. I just took a small subset. One of the things you'll see at the bottom of that table is kind of a odd set of values here, like 373.14, 218.51. It really doesn't follow the same set of numbers like what we had further in the table. And the reason for that is this is pretty close to being the critical point conditions. So the very bottom of the table, it'll tell you the conditions that pretty close to the critical point. This one's not exactly at the critical point, but it's pretty close. Okay, and the reason I know it's not exactly it, because this should be equal to that at the critical point, because the saturated liquid line and the saturated vapor line kind of merge, so you should get the same value. So it's pretty close to the critical point, but not quite. That's why I used an approximately equal to the critical point. So this was a table organized according to temperature, but you can do the same sort of thing organized according to pressure. So this is another saturated liquid vapor mixture table organized according to pressure. So now you see we have pressure on this first column with the corresponding saturation temperature on that column. So just to get us pretty close, for example, close to 1 bar. 1 bar is 100 kilopascals, which is awfully close to the standard atmospheric pressure of 101 kilopascals. But you can see the saturation temperature is 99.61, so pretty close to 100 degrees Celsius. So the same sort of thing, we have the saturated liquid properties, saturated vapor properties. So the same idea, it's just organized a little differently. And again, at the bottom of the table, you have the critical point values. This one is actually at the critical point, and I know that because all of these properties are the same as what you have for the saturated vapor. Again, because when you have the critical point's here. So remember, this is the saturated liquid line right here, This is the saturated vapor line here. So right at the critical point, you should get the same properties regardless of which value, whether you're using the saturated liquid values or the saturated vapor values. So you can see these are the conditions truly for the critical point. Okay, so that's how, again, you find the saturated liquid and saturated vapor values. You'll also use these tables to find property values under the vapor dome, but again, we're going to save that for the next lecture. Now, we still have other regions to worry about, right? So going back up to the picture, we have the compressed liquid region and the superheated vapor regions. So how do we find properties in those? Well, we have tables for each of those as well. Now in those regions, to find the state that you're dealing with, you need the temperature and pressure independently. They're not connected to one another like they are in the saturated liquid vapor mixture region. So here, for example, are the properties for the superheated water vapor table. So we're talking about the superheated vapor region. So let me just kind of sketch that out. So here's pressure, specific volume. Here's your vapor dome. So this is the saturated liquid vapor mixture region. Here's compressed liquid. Here's superheated vapor. We're talking about this region out in here. And let me just sketch in an isotherm for that. So an isotherm would look like that. Okay, so to find the properties in the superheated vapor region, what we do is we look up the temperature. So we have a temperature here, and then each table here is at a different pressure. You can see the pressure varies for each table. So you have to figure out what pressure and temperature you're interested in, and then come in and you can find the rest of the properties from that. Okay, so let's say, let me just arbitrarily pick, let's say we're interested in 200 degrees Celsius and a pressure of 1 bar. Okay, so what I would do is I would come in here and say, okay, 200, well, first of all, I'd say 1 bar, I'd look, here's 1 bar right there, so let me highlight that. So this is the table I want to focus on, this one. And then 200 degrees Celsius, that's right here. So I would come across, and then these would be my properties. Let me box those in. So these would be the properties of interest for those conditions. Okay? And it's helpful here because it'll also tell you the saturation temperature at that pressure. So at a pressure of 1 bar, the saturation temperature, just when we have a saturated liquid vapor mixture, is at that temperature. And you can see our temperature of 200 degrees C is larger than that because it's all superheated vapor in this case. So this is how you'd find those properties. Now you might ask yourself, well, what if I had a temperature instead of 200, what if I had a temperature of 220, which is in between these values? To deal with that, what we do is we linearly interpolate, which I'll talk about at the end of this video lecture. But you just have to approximate it based on the nearest values, the value for 200 and 240, and approximate the value in between. And you can also interpolate between pressures. So here's pressure 0.7 bar, 1 bar. If you had a pressure of 0.9 bar, you would have to linearly interpolate between these two tables. Okay? So that's how you find properties in the superheated vapor region. Okay? Similarly, for the compressed liquid region, so let me sketch the picture again. So PV. Similar picture if you're dealing with the TV plot. So the region we're interested in here is this one. Okay, the compressed liquid region. Same idea, you need 2 properties to identify your state. We have temperature on this axis, pressures in here, and then you can find the properties just from the appropriate table. Same idea as the superheated vapor region. And again, it'll tell you the saturation temperature for that given pressure. So if you're at that pressure of 25 bar, to be a compressed liquid, you're going to have a temperature less than the saturation temperature. If it's a temperature equal to the saturation temperature, then it's a superheated, if it's equal to the saturation temperature at that pressure, then you have the saturated liquid vapor mixture, so it's the 2 phases. And if the temperature is greater than that value, then it's a superheated vapor. Okay. Now, you'll notice that in this set of tables, the changes from one pressure value to the next are actually quite large. So 25 bar to 50 bar to 75 bar, 100 bar, they're pretty big. And the reason for that is because the properties don't change a whole lot with pressure in the compressed liquid region. And you can see that. So here's temperature versus specific volume for water. You can see these are the isobars. So you can see these isobars are going from 220 bar to 500 to 1,000. I mean, they're going in huge step sizes. But as I change, at a given temperature, as I change pressure, I don't really move that far in the specific volume axis, right? So again, this axis is specific volume. I'm changing, as I cross these isobars here, the properties don't change a whole lot. It's because those isobars are so closely spaced together in that compressed liquid region that the pressure has almost no effect. And it does have a little bit of an effect, but it's very, very small. The properties are mainly governed by just the temperature, where I am vertically here. They're not governed much by the pressure. That's really important because that allows us to do some approximations. And in fact, let me just go all the way down here. Sorry, I'm scrolling back and forth a lot. In fact, one of the we have two approximations that we frequently use when we're in the compressed liquid region. One is that the specific volume, which is really a function of temperature and pressure, you can see that from these tables. But in reality, the specific volume is a function of temperature and pressure for a compressed liquid. But it's pretty reasonable to assume that real specific volume is about equal to the saturated liquid specific volume at the same temperature here. The pressure doesn't factor into it. And again, it's because those isobars are so closely spaced together, pressure doesn't really come into play. Similarly, if you looked closely, if you plotted the specific internal energy, you'd also show that even though it's really a function of temperature and pressure in the compressed liquid region, it's very reasonable to assume that it's about equal to the specific internal energy for the saturated liquid at the same temperature. So we'll use these approximations all the time. Very, very common. They just allow us to avoid having to come to these tables and do some interpolation. It's just much easier to work with those approximations. Because then, to get these values, the saturated liquid values, we can still just go back up and work with this table. You can just, instead of worrying about, it's actually this one, instead of worrying about the temperature and pressure dependence in the compressed liquid region, we know it's really just mostly a function of temperature. So you could come down here, find the right temperature, and then just use the saturated liquid values for specific volume and specific internal energy. Now, enthalpy and entropy we'll handle separately. Those, we haven't talked about those yet, so that there'll be approximations for those as well, but we'll talk about them later. Okay, so I think we've covered, let's see if I've covered everything I wanted to. Oh, the last thing I wanted to do is just talk a little bit about linear interpolation. As I mentioned in those tables, there may be some values you need that are in between the value table. So we have to interpolate or approximate what those values are. And linear interpolation is the way we do that. So I'm trying to sketch out the idea of linear interpolation with this picture. So let's say on this axis you have pressure, some property. Let's call it P. And this is some horizontal axis value, I'll just call it V. And let's say that there's a relationship between these two. So P is some function of V. Let me just call it just a regular V. Okay, so this does not, I'm not trying to indicate pressure and volume here. I'm just saying property and value. Okay, I should have just used X and Y. That would have been better. Nevertheless, here we are. So let's say there's some function, property, some function of the value that follows this line here. Let me highlight it in green. So that's the real curve of what it looks like. And let's say I have in my tables the value for that property at some small value. That's the V sub S, meaning small. And so I know the property at that small value. So let's say I know the value here from my table. And I also have the property value at some large value, so that's the VL. So I would say I have this. So I know at this small value what the property value is, and at this large value, I know what the property is. So I know those 2 points from my table. And the actual curve looks like that. Now, let's say I want to get the property at some intermediate value here. Now, the real value of the property is right there, right? Because it's right on the curve. So here's the actual value of the property. When we linearly interpolate, what we're going to do is we're just going to approximate this real curve with a straight line. That's the dashed line. That's the interpolation line. And so when we interpolate, what we're actually getting is this value here, the interpolated value. It's not exactly right, but it's pretty close. And if our VS and VL are pretty close together, then our approximation gets better and better. Okay, but this is what linear interpolation is instead of having the real curve, we actually just draw kind of straight lines in between points. Now, to figure out what that interpolated value is we can just make use of the equation of a line, and that's what I've done down here. So this has the form of like y minus y naught equals slope times x minus x naught. That's the form we have here. Instead of y minus y naught, I have a p for my property. So this is what I'm trying to find is my interpolated value. This is the small value here. Instead of x, I have the value, which is what this is. So this is the actual, the value I'm trying to find the property at, minus the small value here. So that's the x naught. And then the slope of that line will just be kind of the rise over the run. So it'll be PL minus PS. That's the rise. And the run would be VL minus VS. So that's my slope, M. And so in order to find the interpolated value, I would just solve this equation specifically for that. So that's what linear interpolation is. I think you've probably done linear interpolation before, but I think it's helpful to just draw the picture so you can sort of see what actually is happening there. But you'll do linear interpolation frequently when we use these tables. Now, in real practice, like as a practicing engineer, it's likely you probably wouldn't use tables like this. Instead, you would rely on like the NIST database or some computer program that you type in pressure and temperature and it'll give you all the property values you need. But inside that table, inside that computer program, they're relying on these kinds of tables with interpolation going on. Now, we want you to use the tables because when we give you an exam or a quiz, you won't have access to the internet, and so you need to be able to use the tables to be able to do calculations. Okay, so using the tables here, in the classroom, it's just by necessity during exams, but when you get out into engineering practice, you probably won't use these tables too much. You would rely on a computer program that's doing all the calculations within the program itself. But you need to get skilled with it in order to deal with it here in our academic setting. So we'll go ahead and end the lecture there. We've covered a lot of material. It's really important that you understand how to use these tables because the entire rest of the course is going to rely on getting properties from the tables. So I give a bunch of examples on the web page that go through how to find properties and sketch them on these kinds of plots like these right here. So you'll want to go through all of those examples and test yourself to make sure you really understand how it works, because if you can't figure out how to find the properties and sketch them on these plots, then you're going to struggle throughout the rest of the course. So rewatch this video, take a look at your textbook, take a look at the reading notes that I've put together, the text style notes, and then go through the examples because they're very important to get through. All right, we'll end it there.